All right, in class the other day we were discussing several mechanisms of nucleophilic acyl addition. And I mentioned that there were a few of these reactions that were really critical in biochemistry. And so what I want to do is review for you the mechanism of acetal formation. So our reactant is going to be an aldehyde or a ketone. So I'm going to take you through a general mechanism, and then I'm going to give you an actual biological example. And for our biological example, we're going to look at the cyclization of glucose and the polymerization of glucose to make glycogen. So let's first go through the mechanism in a more general sense. Let's imagine that we have a carbonyl like 2-butanone, and we are going to first activate the carbonyl carbon as an electrophile by protonating the oxygen. And so one of the lone pairs of the oxygen atom will abstract this hydrogen, and the HA bond is going to break heterolytically, leaving us with A- as the conjugate base, and the protonated 2-butanone. And what this really accomplishes is activating the carbonyl carbon as an electrophile. So at this point, an alcohol functionality, more specifically one of the lone pairs of electrons on oxygen, will nucleophilically attack this carbonyl carbon. Of course, this pi bond is going to break. And as I mentioned in class, this is going to leave us with what we classify as a tetrahedral intermediate. So we'll have OH, and of course, we will have OR. Now initially this hydrogen is still attached. And to facilitate neutralizing this compound, the conjugate base of our parent acid HA will perform a proton transfer reaction. So at the conclusion of this step, we have regenerated HA, so HA is truly a catalyst, and we have converted the carbonyl functional group to a hemiacetal. That is, the carbon that was formerly the carbonyl is now a half ether, half alcohol. We call this a hemiacetal. The hemiacetal will continue to react with HA unless I very carefully only have a stoichiometric amount of the alcohol that is added. Unless you are given reaction conditions where it is explicitly stated that you only have one equivalent of the alcohol, you should assume that you have an excess and that this reaction mechanism will continue. Now we're about halfway through this mechanism, so let's take a moment to look at the steps. proton transfer in step 1. Nucleophilic attack in step 2. And a proton transfer in step 3. Certainly mechanistic steps that we have seen before. Now let's go to step 4. We'll now have our equivalent of HA and of course we will mediate another proton transfer. So we will abstract the hydrogen atom. Of course, the conjugate base is now a byproduct of this reaction. And I now have a protonated alcohol. Still a hemiacetal, but if you look at this in terms of what's about to happen, we're about to condense this molecule by eliminating a molecule of water. So this step in step 4 is very much like the step in step 1, in which I am activating the electrophilic carbon for nucleophilic attack. And so in step 5, we shouldn't be surprised that this is much like step 2, in which we are going to have a nucleophilic attack. Now, here's the thing. We could imagine an attack that is simultaneous in terms of this attacking and this leaving. That would be like an SN2 reaction. Unfortunately, when we do the experiments, we find that when we increase the concentration of the nucleophile, there's no effect on the rate. Therefore, we have to eliminate this as a possibility. Even though we know eventually we're going to have a second nucleophilic attack, what really happens is we have an intramolecular expulsion of the water molecule. Something that's a little bit different. So what instead happens is that we will form a carbon-oxygen double bond. That's a nice thermodynamic driving force in and of itself. And we will break the carbon-oxygen bond and water will now leave. So the driving force here really is an increase in entropy. And notice what I now have. I have already built in an activated carbonyl carbon because this oxygen will be positively charged. As you might expect, now the second alcohol will attack. And now my carbonyl carbon, or what used to be my carbonyl carbon, is a diether. Now we're not quite done yet because one of these oxygens is still protonated. And so we'll need the final A- to deprotonate this hydrogen and yield the acetal. And so our final product has our former carbonyl carbon as a diether. Now this carbon has a special name. It is called the anomeric carbon. And when this carbon, if these two groups are different, we will now have a chiral center. And this is exactly what happens in the case of glucose. So let's take a look at the case of glucose. And we'll go through these steps again. Now, typically we render glucose in the Fischer projection because glucose has a lot of chiral centers. So I'm going to show you this this Fischer projection. Of course, carbon 1 is an aldehyde. So glucose is classified as an aldehyde, and as we're going to see in a moment, some other things as well. It's also a polyalcohol. And the conformations of this alcohol is very distinct. In fact, as a review of stereochemistry, I think it would be useful for you to assign R and S to all of these chiral centers. And we have 1, 2, 3, 4 chiral centers. So in the mechanism for the cyclization of glucose, which roughly corresponds to our hemiacetal, steps are going to be very much what we've just seen. First of all, one of the lone pairs of the carbonyl oxygen will abstract a hydrogen atom. So our first intermediate will simply activate our carbonyl carbon. Of course, we want to fill in all the details that we had previously. If you allow yourself to kind of go back to when we discussed conformation, not all rings have equal stability. We know that 6-membered rings are the most stable, quickly followed by 5-membered rings. And so we have the necessary alcohol nucleophile within this molecule to do a cyclization that's intramolecular. So let's look at this oxygen and let's call this atom 1, 2, 3, 4, 5, 6. This is the best nucleophile because it's going to give me the most stable ring system. And so lone pair attacks the electrophilic carbon, and this bond will now break. What this is going to accomplish is best rendered in the chair conformation, because it's a 6-membered ring. And of course, my anomeric carbon, which is carbon 1, is right here. And notice that this OH can either be axial or equatorial. Typically, equatorial is more stable. We'll be learning about that in class very shortly, which now means the hydrogen is axial. Beautiful thing about glucose is all the hydroxyl groups are equatorial. Very easy to remember the most stable conformation of glucose. This is not the same for a lot of other carbohydrates, by the way. So carbon 1, 2, 3, 4, 5, and 6. Carbon 5's OH is right here. Also, the OH that attacked is protonated. So this has a positive charge. And as we know from our previous mechanism, simple acid-base proton transfer step is going to neutralize this to the full hemiacetal. And so our structure after the first half of this mechanism is as follows. And we have the cyclic form of glucose, which accounts for about 99% of all glucose in the human body. So in vivo, this is how glucose appears. Now we're not quite finished yet. Let's look at how we can link two glucose molecules together to go from a hemiacetal to an acetal. So this molecule would be a hemiacetal. Again, the anomeric carbon is the only carbon that is both an ether and an alcohol. So we'll start with the hemiacetal, and now what we're going to do is take the HA that we generated at the end of step 3, and we're going to protonate this OH. Of course, you guys are probably going to have to refamiliarize yourself with drawing the chair conformation. There is another conformation called the Hayworth conformation that we'll have to master. For those of you who are going to be transferring to the University of Memphis and taking bioorganic, you will have to translate a Fisher projection, a chair conformation, a Hayworth conformation in and out of one another. So it's going to be a very important skill for you to learn. Model kit definitely helps seeing this. And so now we're going to have the carbonyl oxygen will facilitate this elimination reaction. Now this is a bit misleading. The structure of this ring will actually look more like more planar. So you have an extra carbon right here, and right here. But in order for us to visualize this, I'm going to keep it in this less realistic conformation. By the way, this is a real nice application of conformational analysis that we learned about this time last semester. And of course, I'm missing all my other substituents, so let's go ahead and put those in as well. And so now imagine having a second glucose molecule and it just so happens the way that these disaccharides are made in nature and biological systems, again, if we label our carbons, it is the 4-hydroxyl that attacks our carbonyl carbon, which of course is going to lead to you can have a choice here. Typically we'll see this in the beta conformation, which means equatorial. I don't think that really should be a big surprise because equatorial is typically thought to be more stable than axial. Since this is carbon 1 and this is carbon 4, this is called a 1,4 beta linkage. And this will become a lot more relevant in, well, for some of you in your medical school courses, for others of you in a bioorganic course or in a biochemistry course. This is a 1,4 beta linkage, and it's glucose beta glucose. And we will discuss these types of structures to a very large degree when we talk about carbohydrates on Thursday and beyond. Now, one of the interesting things about carbohydrates is that this carbon is no longer in equilibrium with its aldehyde. I cannot revert this back to the aldehyde. A hemiacetal, on the other hand, is in equilibrium with its aldehyde, and as long as your sugar has one residue that is in equilibrium with its aldehyde, it is termed a reducing sugar. Sucrose, on the other hand, as we'll discover when we discuss carbohydrates more formally, is not a reducing sugar. So it only has an acetal linkage, not a hemiacetal linkage. Glucose beta glucose. So here's a very nice application of this mechanism. Of course, we will also have a deprotonation step that we need to undergo. This will be protonated, but of course we know how that's going to unfold. A minus in the last step will promote a proton transfer, and that yields our final product. So here's a very nice biological application of the mechanism of making an acetal. In the next podcast, we'll talk about how we can use acetals as protecting groups in organic synthesis.